screen. So you can see over there. All right, we are warming up. We start at 9:30. Let's see how many watchers will be in the pool. 9:30 is the start. Now it's just to let people connect. I have the class, like 5 people in class. So, yeah. Now 2 concurrent viewers. One is Omar that is checking. Now I do try the switch of the screen so that we also measure the lag. Sooner or later you should be able to see. If this is visible, then otherwise I have to. Yeah, yeah. Does it work? You see, it works. All right. And also my little ugly face on the corner. Very good. Oh, 8 concurrent viewers. And now we're waiting for 8:30. If you, meanwhile, you have questions, post them in the chat, and I will somehow answer. So, this 4 minutes should amortize the delay. So what I expect in this lesson is that you are at least aligned with the previous episodes, because we will build from there. I have 3 minutes. The audio. The audio is fine. Yes. Sa. Yes. Sa. Sound check.
L'almost done di che dire se il prototype voleva spiegare sul riporto che c'è almost done.
Oh, I'm receiving a almost. Let me see what you're seeing.
Last comment.
Raw. No, because I'll work on the other account. Source RP 07KD3. Okay, yeah, that was it more or less. We will have fun, modifying the things. All right, so 29, we're almost there. No people are talking. So we can start the semi-last lesson on basically C++ syntax. And then this time we will also see the example constructed from scratch, because I think that seeing an approach to synthesis, seeing someone doing an exercise from scratch, helps you thinking. We will also, we will do it together, by the way. I will try to do this. So I will present in the lesson. Shift F5. I will present in the lesson a way, an algorithm and a data structure to respond the question, and then together we will translate what we will theorize into a C++ program that solves the task using all our nitty-gritty generic things and investigating the choices. So this is my plan for today. All right. As I mentioned last lesson, in our domain, shall it be artificial intelligence, shall it be geometric perception, or robotics in general, like task that you typically are required to solve is to find the closest vector to a query one. So I give you a query, and I give you a collection of vectors, and I ask you, can you retrieve, please, the vector in the collection that is closest to the query, right? This is, for instance, the case when you want to do some visual recognition thing, old style, or some contemporary Islam system, where you typically have an image. From the image, you extract a set of interest points called key points, like points like corners or whatever. This can be done by morphological operations on the image. And then you characterize the appearance of each of those points, of the image around each of those points. Like means consider a tiny little image centered around the key point, and you extract through some algorithm something, a descriptor vector that encodes the appearance of this region of the image, right? Then if I give you another image, I might ask you, hey, what are you extract the key points once again, you extract the descriptors once again, and I might ask you, hey, can you find which point in the first image is similar to which point in the second image? And then you do this on an appearance-based fashion by comparing the descriptors. That is, you consider all descriptors extracted from the first image, all descriptors extracted from the first image, and then you try to look for each of which one in the other image is the closest. You have a match, and then if you have a match, then you can do funny things. Like, for instance, reconstruct the motion up to a scale. Okay? But the bulky operation is typically find the point in a set of the vector, in a collection of vectors, let's call them Pn, with n going from 1 to n, each point lying in a space of Rk. Now in our examples we will stick to R3 because they are easy to visualize, or R2, but they could be also Rn, with an arbitrary dimensional descriptor vector, because the descriptors, for instance, they do not have meaning in the Euclidean space, they're just numbers, okay? But it's also helpful to imagine them geometrically. And also, another thing that I have to give you is a distance metric, so a function that given two of these, given a query vector and another vector, is able to compute a scalar, positive scalar, that is the distance, okay? Because you might have different distance metrics in general. And the problem is like, I give you a query vector, please find me the point. We can solve two classes of problems. First class is, I give you a query vector and I give you this collection of points. Please find me the point in the collection that is closer to the query. The one point, there will be a minimum, or maybe there will be two minimum with equal distance, but then you return just one of the two. And the other question that we might want to answer is, I give you a query point, and then please consider a ball, a distance, not a sphere, like maximum distance. Return all the points in the database, the collection, that are enclosed in this ball having radius d. Okay? So all points whose distance is smaller than a certain epsilon over here. Also, this is useful. Okay? So we can resolve two classes of problems. Now, typical distance metrics, and typical distance metrics are the square norm, like where basically you consider the dot product of the difference between a point pi, let's say the query, and the point pj. So this is like the vector difference, and then you consider the square of the norm. Why don't you take the square root? Because the square root is expensive. And even given that the distance is monotonic, which means that it's constantly growing, I don't care whether I work with the square root or I work with the square distance, square norm. Is that clear? Another classical metric that you will encounter in those of you who will select probabilistic robotics, you will encounter is the so-called omega norm. That is a variant of this square norm, where basically in the outer product of the two vectors you put a scaling matrix that scales differently the components of the vector difference. I will not talk much because we will not use it in this course, but it's another norm. Omega is a symmetric positive definite norm that acts by scaling the components on the distance vector in a different way. For instance, if you have two-dimensional vectors and you are just interested in calculating the metrics on the first component, the distance on the first component, you might have an omega matrix that has 1, 0. In this way, you will delete the difference on the second component. Because when you do P1 times omega times, so the delta, where delta is this difference over here, times omega times delta transpose times omega times delta, then you will cancel, if you do the calculation, the component y, the second component of the vector. But this is just for completeness. Another example of distance is the Hamming distance that is typically used when you have descriptors which are binary. So in image, in computer vision, let's say 2010, in the year 2010, the decade 2010, it was quite common to extract descriptors from the image that were not floating point values, but they were vector of bits, 1, 0, right? And then in this case, how do you compare vectors of bits 1, 0? A common matrix to compare the difference is to consider two query vectors and to report the number of mismatches. So the number of times that in the first vector one bit was 1 and the other bit was 0, or vice versa. Two vectors are the same if the number of mismatches is 0. And the number of mismatches can be considered the distance between these two binary vectors. This is the so-called Hamming distance, and this is an example, no? Like here we have 1, 0, 0, 1, 0, 0, and here 1, 0, 1, 0, 0, 0. You find that here I have a 0, here I have a 1, so this accounts for 1. Here I have 1, here I have a 0, and this is account for another 1. So the Hamming distance between these two is what is these two vectors is 2. Okay, now, so said, the problem looks spectacularly simple. I give you a collection of vectors that could be stored in a container, and I give you a query vector. Then what you could do is to, each time I ask you to do a query, you take this query vector, you measure the distance between this query vector and another vector in the set, and then if the distance is smaller than the distance previously calculated, you say, oh, this is the current best, and then you continue, basically, you do a minima scanning. You continue through all the set, okay? You do an exhaustive search. Is it clear? Now here, it's not part of the KD3 lesson, so I think I've written an example for you. KD3 test. And then I will have the usual fun in changing the font. I don't know why it doesn't options. I can use so options. Now, set default font. Now, set default font. Options. What? What do? Not responsive. G. Jobs. Editor died. FG. Ctrl C. No. Die. No. Boop. And Emacs is pending. Close terminal. Okay, KD3 test. When I have OBS running, it's suffering a bit. Options, set default font. Ubuntu mono regular. Yeah, of course, atomic. Options, set default font. This, select, and then save options. Now, at the 7th lesson, I managed to save the option. This is how I would construct a brute force search, right? Now, let's say I I'd like to think about how a brute force search could work and what it could, which responses it should give. I mean, in general, I'm interested in the more complicated version of the brute force search, which basically responds to the question, I give you a query vector, I give you a collection of items, and I give you a norm, distance, and then I'm interested in you finding filling in this response with all the points in the set for which the distance between the query point and the point itself is smaller than the norm. Is that clear? Now, it sounds quite nice to me to provide you a brute force search, an interface for the brute force search that operates on a range. Why? Why so? Because operating on a range, I think it's quite elegant, because it means that I can have a huge vector where I store all my data, and then I tell you, hey, work in this range rather than in this other range. Okay? How do I provide you the range? I provide you the range with an iterator type, with two iterators, actually, the begin and the end. Okay? Then I'm also interested in returning you the values, the response. So I need to think about a data structure suitable to contain the response. Now I have an option. I could construct a vector or a list or whatever it is, a structure that supports sequential insertion. I could construct a vector that contains the items that are in the set, right? But the items can be arbitrarily large. I might have points which are, let's say, 128 dimensional or floats, or 256 dimensional. Okay, guys? So it's not elegant, given that once I return you a point, I'd rather, it's admissible, but it's not elegant to me. I'd rather return you the pointer to a point in the center. Okay? Therefore, I define the type of answers to be the type of a vector of pointers to the elements in the collection that fulfill the condition that the difference between the query point and the point is smaller than norm. Okay? Well, very good. And then, therefore, we can construct the signature of our function, which is how do we call it? First of all, we reason, what are the type-dependent parameters? The only type-dependent parameter in my function, in order to extract all other types, is the iterator type, because from the iterator I could extract the type of the contained element. From the type of the contained element, I could extract the scalar, assuming that the type of the contained element is a vector. And from the type of the contained element, I could define the type of the answer. Is that clear? Therefore, that's the definition of the method. We start by specifying the type-dependent parameter, which we call it iterator type. And then the signature will work as follows. The first argument, which we call answers, will be a vector. Will be a vector. Why not a list? Your business. I just made it a vector. I could also make it more generic, but I mean, be careful. Could be a vector, was element R, you take the iterator, you extract from the iterator the type contained in the iterator, like which is the item type. You extract it by saying iterator type, which is this parameter, this parameter over here, this template parameter, and you say, please give me the type contained in yourself, which you referred inside the class with using value type. Okay? We have seen it in the last exercise. Of course, the C++ compiler is not smart enough to understand that this is a type, and so you have to write type name in front. So the first argument is going to be a reference. Here you have the reference. To a vector, which contains pointers to the points contained in the range. Okay? That's the first type. Then the begin and the end are easy because it's iterator type. Then we need to provide a query point. The query point should have the very same type of the items stored in the set. And what is the type of the items stored in an iterator? Iterator type, value type, a point. And that's going to be the query point. Of course, it's const because we're not modifying it, and we pass it by reference because we don't want to copy it on the stack. And the final thing is we have the point, the point type, basically. In the set, we have to provide the norm, but the norm is a scalar. And how do I access the type of the scalar? I just like investigate into the structure. We have seen the eigen types defined inside the using scalar for defining the scalar element, and I have this scalar here that I call norm. That clear? And that's the signature of the thing, of the function. Sounds bulky, but everything stems out from, once you understand the game of the nested types, I give you a nested type and you extract from this nested type all other types that are inside. Just think about this type name, column as type members of a class. Okay, guys? And then here I just do some cosmetics. I just like want to say using scalar so that I can see a scalar, and I extract the scalar. I could have left all this huge thing, but I just like do a favor to myself, and I rename the scalar type of the iterator, of the value type contained in the iterator type as a scalar. Then I say square norm because I take, just for symmetry with other methods, I just pass the Euclidean norm, so the square root to this thing, and I calculate the square inside. Okay? Then once I do the game, well, the function will return the number of matches. I iterate over the set, so like I define an iterator that ranges from begin to end, and then here I extract the contained element from the iterator, the point, no? Why do you, so if I take an iterator and I put a star in front, I access to the element pointed by the iterator. And I extract what? I extract auto ampersand extracts me the reference to the iterator, which is to the point, which is the point itself in memory. And then if p minus query is smaller than square norm, so if the difference, I take the point, I subtract it from the query, and then I have the delta vector. And then Eigen defines a function that calls a square norm that calculates p dot p. I calculate this. If this value is smaller than square norm, I push back the address of the point into the answers, and I increment the number of matches. Okay, guys? And I return the number of matches. That's an implementation of brute force, seen step by step. Okay? Very good. See if I have questions. No more? No one? Very good. And it's generic. It works on any type of container, on any dimension of point, and on any type of scalar. All right. And compiles statically. All right. That was more or less the trivial approach. It's only complicated in syntax from the point of, because we wanted to have it generic. But if you wanted to do it on a defined type, it's trivial. No, it's just take from this to this, if condition, put address instead. All right. Now, the problem with this, if you have 2 million 2 million points in the query, and you have to do 2 million searches, then you have 2 million to the square operations that you have to do. Because every search requires scanning through the whole set. And this is, I wouldn't even consider writing a program that having to do this amount of searches would do brute force. I would not even think about it, because even if I test it, it's going to be super slow. And this is an algorithmic thing that goes beyond the language. Of course, if you do it interpreted language is going to take maybe a factor of 100 or a factor of 1,000 longer. But still, we're talking about a quadratic explosion, and we don't like quadratic when we can avoid it. Okay? Let's go if we can go logarithmic. Like in your computer science classes, you might have, or not only computer science classes, because now I'm referring also to the people that are not strictly computer scientists, but I mean, just like think about searching the name into a phone book, which is unordered. It's a pain, right? So like the idea is that, but normally, like what do you do in a phone book if you are a computer to search an address? Like you're given a name, then you take the phone book, you open in the middle, and then you look if the name is smaller or larger than the first name on the page in the middle. If it's smaller, then you go in the other half, in the first half, you open it at half, and then you repeat it. Right? That's so-called binary search that induces an ordering in the structure. So our idea would be to order the points, okay? In a way that the search is faster. I mean, how long would it take this process to converge? Well, each time you carry on one step, you halve your search set by 2, which means that you will need a logarithmic number of searches. Okay, it's good. The problem with this schema is that it relies on the strict comparison. So, am I larger or am I smaller? How can you say whether 2 points are one larger or smaller than another? You can't, because they have multiple dimensions. They are not ordered, that they lie on a plane. While on a line, you can tell which point comes first. On a plane, on a 2D space, which one is coming first, then another? So you can't do directly a binary search. However, we could invent a matrix that establishes the mid pages of every part of our points. And that is the game basically of KD trees. The idea is the following. I give you your set of data points, right? And then you could decide, you could find, if I give you a set of data points, you could find 2 things. You could find, if I give you a set of data points, you could find the point which is in the middle, no, of all the set, or not necessarily a point which is in the middle, but you could find the mean of this distribution of points, right? And then we can also say, given that if we want to split, the easiest way to split is to cut the point through a plane, this cloud of points through a plane, right? I already tell you that a good point, it's also sensible, that a good point where to cut off this set of points is the midpoint, okay? For 2 reasons. First, because if you cut through the midpoint, you will more or less have 2 balanced subsets, because you're cutting through the middle. So the number of points that will lie on the one side of the plane would be more or less the same as the number of points that lie on the other side of the plane. Because if this distribution would be unbalanced, then you would have too much elements on the one side, and then probably you wouldn't be logarithmic anymore in the search. Okay? We all agree that the splitting should occur through the mean of these points. And then the other question is, okay, I want to split this distribution of points. And in order to split this distribution, this set of points, I cut them through the mean with a plane. And there is another question. How is this plane oriented? Because, okay, I fix the mean. Can I choose any arbitrary random plane? Up to a certain point. Just imagine that you have points which are very densely distributed along a kind of a line, something like that, no? Along, this is point, all here. Do you see it? All right. Now, let's say, if I cut them in the middle this way, Do you think it's a good idea? What is the best idea to cut this point so that the two sets, the two portions will be as far as possible from each other? It's like cutting through the direction, cutting with a plane that was normal, lies in the direction of maximum variation of my point distribution. Let's say I make you another example. Assuming that I have a point distribution where I have a bunch of points here and a bunch of points here. Let's see if I'm visible. Yeah. Yes. Where I have a bunch of points here and a bunch of points here, right? Now, what would be the direction of, what would be the mean? Well, the mean would be more or less here in the middle. Okay, guys? Now, if I would cut this distribution with a plane like that, I will have a little bit of this cluster and a little bit of this cluster cut through the plane. And this is not what I like. What I would like is to have the clusters well separated from each other. Okay? And then, therefore, to me, it seems a very sensible choice to cut with a plane that is passing through the mean of the points and that has a normal oriented towards the direction of maximum variation. Okay? But the direction of maximum variation is super easy to determine from a set of points. Because as you might have seen from other courses, the direction of maximum variation is nothing else than the eigenvector corresponding to the largest eigenvalue of the covariance matrix. So you have a covariance matrix. The covariance matrix is a symmetric positive definite matrix that therefore admits an eigenvalue decomposition. The eigenvalue decomposition factors a matrix into a rotation matrix and a rotation matrix transposed, and then a diagonal matrix of the eigenvalues. You pick up the eigenvector, so the column of the rotation matrix containing the eigenvectors that corresponds to the direction, to the largest lambda, the largest vector. I think you have seen it in geometry 1. You remember something about eigenvalues and eigenvectors? Well, the point is that I'm not teaching you how to calculate the eigenvalues and eigenvectors because this requires the SVD decomposition, but one day, if you're interested, I will talk about it. But the good thing is that Eigen offers you a method that, given a square matrix, calculates the eigenvectors and calculates the eigenvalues. At this point, you just like pick up the largest. Okay? And this is given by me in the example of last time. In the covariance, there was the last line that I said, oh, here, this is the method that, given a covariance matrix, extracts the largest eigenvector. With largest eigenvector, I mean the eigenvector corresponding to the largest eigenvalue. The eigenvectors are all unit norm. Okay? Clear? All right. Now, coming to the data structures. We already understood that we would like to organize these points in a tree, right? And how do we do this? Okay, we have our initial set of points, and then we calculate the split plane. Okay? This initial set of points will be the first node of my tree. This first node will be characterized by a normal of the plane and by a mean, which encode basically the split plane. And then on the left leaf, I will continue constructing the tree. Well, I will have, on the left leaf, I will have another tree structure, but that will contain all the points that lie on the one side of the plane. On the right leaf, I will have another structure that will contain all the points that will lie on the right side of the tree. What do I do with the left leaf? Well, the left leaf on my binary tree will be obtained by running the same process. So I take this subset of points, I calculate the mean, I calculate the covariance, I extract the smallest eigenvalue, I define a splitting plane, and I continue the partitioning. Okay, do you visualize now the process? Now, from an algorithmic point of view, this is I would say, if I give you the eigenvectors, I give you a split predicate, I give you a plane side predicate, they should be quite, should be tickling of doing it, and we will do it together now. What is important to think is that each split plane is characterized by a normal, a mean, and that's it, and potentially the containing points. In the last nodes of the tree, I mean, actually, like going on and doing this search is efficient as long as the number of points is large. At a certain point, if you have a search structure that has, let's say, a subset that has, let's say, 20 points, and in this case, it's not any more convenient to do when you do a search to do the recursion, to go to the left, to the right, and so on. If the number of points is small enough, then it's convenient that you do a linear search, like the brute force search that we have seen before. Okay, because it's going to be an extremely fast operation for the machine. So normally, in a real implementation of KD3, divides, let's say, the type of nodes in the tree in two classes: the intermediate nodes, which contain a split plane and contain a split plane, so mean and normal vector, and then pointers to the leaf nodes. And then we have the leaf nodes, so the terminal ones, that will just contain a range of points where, in case of search, a brute force will be conducted. Now, in the action of doing a search, how will a KD3 work? I give you a query point, you have the root of your tree, and then what do you do with the root of your tree? You ask to the root, hey, are you on the left or on the right of the splitting plane? If you are on the left, then you continue the search on the left. If you are on the right, you continue the search on the right. Okay, guys? And then, so long, you can do it, and then you continue until you reach a leaf, and in this case, you do a brute force search. Okay, guys? And the number of operation is roughly logarithmic. If you render the number of points in the leaf upper bounded, then you can upper bound the complexity of this operation with a constant, so it's dominated by the search in the tree. Okay? Now, there is one problem with the KD trees, that the search is not complete. What does it mean that it's not complete? That a KD tree, in case you ask for all points in a ball, might not return all the points that would be returned by a full search. To visualize the reason, just think, in case I have two sets of points, I have a set of points like a certain distribution of points, okay? Then imagine, unfortunately I don't have a blackboard, so I have to visualize. But imagine, just draw some points in your problem. Then you decide to split them. Let's imagine that we are in 2D, so a splitting plane is going to be a line. No? You split with a line like that, right? Then I ask you a query point which is immediately on the right of the line, just because the mean is a point which is invented. So immediately on this side of the line, right? And unfortunately, the closest point in the set would be on the other side of the line. Just because the split plane is cutting through them, and the way you construct it didn't take into it's just considering a cumulative appearance of the points, right? And so if you have a little point here, it would be the closest one. But unfortunately, in the search process, at the beginning you said, oh, this point lies on the right of the KD3, or on the split plane, so I'm going to the right. And once you go to the right, or to one side, you never go back, okay? This is the problem of the KD3. So it's not complete. It's correct, because in the end, correctness means that if it returns you an answer, that the answer is, that verifies the predicate, like norm smaller than that, but it's not complete. It doesn't return you all of them. And also it becomes not correct in case you're interested in having the closest one. Because if you are interested in having the closest one, then it might return you a closest one, which is not the closest one. Okay? Luckily, and now you also understand the importance of our criterion in choosing the split plane in a way that it separates the maximum the two clusters. Because in this way, we have split plane that in theory is far enough from the data points which are contained in the two halves. Okay? We could, however, render the search complete. This was something I was thinking the last days, and it's possible. We pay a price. How would you render the search complete? I mean, that's once you calculate the split predicate, the side of the plane, an information that you have is typically the distance from the split plane, right? Because you basically the distance from the split plane. In order to get the distance from the splitting plane, you take the mean of the plane. You take the query point, which is here. Then you have the vector between the mean and the query plane. If you project this vector onto the normal of the plane, you get the distance between the point and the plane. If the distance is positive, then you lie on one side. If the distance is negative, you lie on the other side. Now, this critical condition on this incompleteness arises by the fact that you don't consider the distance from the point to the split plane when doing the search. Like, once I do a query, when can I have incomplete search? I can have incomplete search if the distance between the point and the split plane is smaller than the ball where I'm searching for. Because if the radius where I'm searching for is smaller than the distance between me and the split plane, this means that this ball is sliced and a part of this ball might lie on the other side. Do you see that, guys? Now, in this case, it would be making perfect sense to have to conduct the search in three ways. Take a point, measure the distance between the point and the split plane. If the distance is larger than the norm of the ball, larger than the norm, then continue the search on the right because you're sure you're not in the critical condition. If the distance is smaller than the norm, right, the minus the norm, then this means that you are on the other side of the split plane. If the distance is equal, if the distance is between minus norm and plus norm, this means that you are in a critical condition. And in this case, the result of the search will be the result of the search on the left and the result of the search on the right. You unite them. Okay, guys? And this renders the KD3 complete. Of course, it comes at a cost, and this search would degenerate to a full search in case the query of the ball is too large, but we can live with it, right? Now, let's go to the design of a KD3, and we will now design a generic KD3, and I will try to code it from scratch. Okay, guys? Let's see if there are questions here. No questions? Very good. Okay, 1008, yeah, you can make it.
Sorry, but what if I'm looking for the closest point? What if I'm looking for the closest point?
Same story.
But then I'd like to put this epsilon like arbitrarily.
No, you know the range. When you're looking for the closest point, you're looking yeah, your colleague says. What if I'm looking for the closest point? Normally, in these search structures, you are interested in responses was distance as a maximum distance. Because if you get a point which has absolutely no meaning, that it's in the blue sky, even if it's the closest, you say, no, I'm not interested in. So that's if you're interested, in the worst case, if you're interested in the closest point in absolute without radius, then yeah, bad luck, right? You will find it anyway, but that's not normally what you want to find. In a descriptor, when matching descriptors, you are interested in descriptors that are close enough. If two descriptors don't match at all, you don't want to find, oh, this descriptor is closest to this, because they refer to portion of images that are completely different. But normally, like this, we are interested in the best match among those that have a distance smaller than a value. Okay, let's see on what can we leverage. Do you remember the split function that we have talked about? Yes? Okay, we will leverage on the split function, that generic split function that we have seen before, that takes an iterator begin, an iterator end, and it takes a predicate, right? We will leverage on the split, no, plane side predicate, on the plane side, not sides, side, side, oh, side predicate that tells whether, by giving the center and the direction, no, mean and smaller eigenvector tells you on which side of the plane a point is. So this is on construction, assigned on construction, and this is the operator bracket that conducts the evaluation. Okay? And also we will leverage on covariance.h, the horrible covariance thing that this time should become more digestible after all the explanation on the type names and whatever. And the pain comes from the problem that I'm not able to define usings here, right? That inside the arguments of a function. But this basically is oh, it's really ugly, guys. Okay, try to make it readable, but never manage. Okay. Okay, first argument is the mean, that is defined over a field of scalar, rows at compile time 1. Second argument is the covariance matrix that extracts the rows at compile times from the matrix. Remember that rows at compile time is a static constant defined inside the type, and then we do our funky calculations. Okay? Clear? Of course, here I use the fast calculation of the mean. And the other thing, the other function that I was defining is, try to make it readable but don't succeed, a function that calculates the largest eigenvector. Now, of a square matrix. What is the largest eigenvector of a square matrix? Well, it's a matrix that has defined on a field scalar that you obtain from the square matrix, and that has a number of columns of rows equals to its square, which is equal to the rows of the input matrix, and it has a number of columns which is 1. And then I was Googling on how to determine the largest eigenvector. I wrote the method largest eigenvector of a square matrix types that does what Eigen provides me already to do. Okay? So I was looking at the documentation. This is a copy and paste from the documentation. Invoking this method on a matrix returns me the largest eigenvector. Okay, guys? I mean, I didn't, it's not that you have to know it. You type how to compute on Google, how to compute eigenvectors, symmetric, positive, definite matrix, and then you find the answer. You take the example, you copy it, and that's it. That's it. All right. This is what we can leverage with. And then let's start constructing my funky predicate KD3. Include, now I don't have a normal keyboard, so I will suffer, split. No? At least we have to include the split file. And for sure we have to include how was it the other one? The plain side predicate. Told you that without proper keyboard I will suffer. And for sure we will have to include the eigencovariance. What was it called? Right. Now, our tree, I will also use smart pointers. how would we construct a tree? Well, what should a tree contain? And how should a tree be defined? A tree should be defined on a range. The tree is its node. So we're now constructing a data structure that it's containing the three elements, like the nodes of the tree. And I like it. I would like that the only template parameter that I pass, the only type that I pass to my data structure, should be the iterator type of the iterator type of the range that the tree will contain. Okay, guys? Or class. Let's become. Then let's put some variable. Or before the variables, I would just extract some type from my iterator. Okay? Any help? And I have extracted the type of the point. Scalar. Static. And I'd like int. And I'd like also to extract the dimension, because the points have a dimension and I might want to have it for calculating the covariance. This is a constant defined at compile time, so I can say const x, dear compiler, evaluate it right now. And I know that if I say point type rows at compile time, I extract this static variable of the class point type. Okay, guys? Then also it makes sense to define mean, a matrix type to store the covariance, just for me, for my eyes. Does it make sense? Do I have all my types in order? Very good. And then we're going to need to store something into this node. So now here we have only defined the types. We didn't define the member variables. Now we need to put the member variables. And what will we have to put? The mean. What is the type of the mean? Mean. The mean. The mean vector. Point type is the mean. What bugs you? Otherwise, how I can subtract a point from its mean if one is a vector and the other one is a scalar? Okay. What is the normal? The normal should support the normal of a plane is a vector that has the same dimensions of the mean. Right? Okay. Do we need anything else? Well, we have said that our tree node will contain a range, right? Minimum, maximum. So we might require to have two iterators, one at the beginning and one at the end. A iterator type. Iterator type. Just I will redefine it for me. So like here I have defined an iterator type that I extract from the parameters. Because once you are out of the template, you lose these parameters unless you have taken a using. With this game, I will be able to take it later and then to extract the iterator type that I passed during the definition. But let's be a little bit less verbose. Okay? Also, I'd like to use the automatic memory management for my potential, my children, like the trees, the subtrees, because this might be a node in the middle, right? A node which is not a leaf, a mid node, right? So if I want to use automatic memory management, I have to define a smart pointer constructed on the tree node. Okay? So I could define it. It makes sense here to use a unique pointer because once you construct a tree, the tree is frozen. It's not because it binds to the set. You don't want to do copying of this thing. You at most once you construct it, you pass it by reference, but that's it. It's not a data structure that you copy, and it's convenient to use unique pointers. Now. To this class over here. What is the class? Could I write tree node here? I have to specify on what is constructed the tree node. Or I could be more gentle. Or tree node. Well, normally I use always this type equal tree node of iterator type, and then here I write this type. I define. Oh, this is the 0. It's nice. It's there just to confuse you. Of course, then here I will have. Okay. Very good. Then, are we done? We need in terms of data, I think we're done. Then we can proceed and define the constructor. The constructor of a tree node, which will be the one. What do we need to pass to the constructor? We need to pass to the constructor the beginning, clear. The end, obviously. And thanks to the way we defined our split predicate, we know that the split predicate will shuffle the points inside the set in a way that all the points that satisfy the predicate will be at the beginning, all the points that don't satisfy the predicate will be at the end, and the split element will be the midpoint. So we don't need anymore to store the points in the tree. We will just pass the range, because during the construction of the tree, at every splitting, we will rearrange the point on the left and on the right side in a way that everything is consistent. So we don't even need to replicate memory. That's the design thing. Do you understand the game? The split orders the points. All the points in a set are of one color, or the other points are in another color. And this way, this subtree will be entirely characterized by a begin and the middle. The right subtree will be characterized by the middle and the end. Okay, guys? Very good. Let me be consistent second with the signature that I used in the solution, because otherwise when I run the test I will have issues. Normally I'm self-consistent, but KD3 H 1 dinner. Here on the container I've parameterized it. Oh. No. Yeah. Well, I've done it on the iterator, I liked it more. Begin and the max pointing leaf. Perfect. Okay, guys? It's like in the constructor, I pass the following parameters. I pass a begin, the start of the range, and then the end of the range, and also a maximum number of points after which I don't want anymore to continue the splitting, and I'm gonna create a leaf. Okay, guys? Very good. Now, what do we want? Left and right, these two elements over here, are automatically set to 0. They are null pointer on creation. So once we create a node, this node is going to be a leaf by definition. How do we distinguish whether a node is a leaf or not? We can just check whether left and right are null pointer. If they are null pointer, this means that it has to be a leaf because it doesn't have children. Okay, so we don't need to do is leaf, is not leaf. Just look at the left and the right, and you go ahead. Now, I think that there is a way on the STL to count the number of elements. STD distance. That is this function that returns you the number of points. So, on construction, it makes begin like this and end like this. On construction, makes a lot of sense to initialize the begin with the begin and the end with the end, so that I have the ranges consistent. Yes? All right. Poi, yeah. Do you agree? I mean, of course, instead of, I could have also used the counter, no? For auto it equals begin, it not equals end, and pew it. Could have also done something like that. This is the traditional way, but I found that in the STL there is the STD distance. Let's use it. Okay? All right. Then, first thing, if the number of points is smaller than a leaf, we don't need to do anything, right? Done. We are in leaf, we set the begin, we set the end, we don't need to do anything else. Agreed? Because it's a leaf. We already stored the begin and the end, and that's it. Okay? And then, now we are in the bad case, the case where we have to compute the mean, the covariance, and then proceed in the recursive construction of the tree. All right. How was my function compute eigencovariance? Compute mean and covariance, perfect. Mean, covariance, no, iterator, no, was like mean, covariance, and then begin end, perfect. how did I call it? I have to define covariance type, because I don't have the covariance in my class. I don't need to store the covariance in the node of the tree. I only need to calculate the covariance temporarily on the point in order to extract the smallest eigenvalue, the largest eigenvalue. Right? The mean, I just store it straight away in my data element. The covariance, I will manipulate it later in order to extract the smallest eigenvector. Compute, no, how was it? The method, largest eigenvector. And I have it. At this point, in order to continue the splitting, I will have to call the split on the split predicate. Agreed? And then open the split predicate. Split, not the split, split. Split takes begin, end, and the predicate. And the predicate is plain sight predicate. Plain sight predicate.h. Okay, perfect. Well, what was the buffer? Was my funky KD3. So normally I work with a screen where I see more than one element, so I'm a little bit confused. So iterator type. Did I save the yes, iterator type? Remember that the split predicate returns me the iterator to the mid element, those that splits the things in two. Split, and then begin, end. What was it? Begin, end, and then the predicate, plain sight predicate of point type. Mean, normal. I have the iterator to the mean. Not only, by doing the splitting, I also rearrange the elements in the set between begin and end. Okay? In this way, I didn't create any copy. At this point, I can go on and I can say, okay, I have a middle. The right pointer is a new tree, and the left pointer is another tree. Begin. Middle, I'm missing something. And also here I'm missing something. This middle, end, just to make it symmetric. Begin, middle, middle, end. Okay? Done. We have done a KD3. All right? And then we have to implement the search. To have it consistent with the other search function, we might need to define an answer, a type of answer, right? That we would like to have this data structure returning a vector of pointers to points that contains the answers for the search. Okay? Makes sense. It's elegant. Hmm? Yeah, fast search. And in the fast search, we have to pass. We are constructing a function that is a fast search that responds with a vector of answers, right? No, answer type. Remember that we pass a vector and we want the function to fill it in. Okay? Then we need a query point. How did I do it in the brute force search? Where was test? Maybe here. So the answer begin, end, query and norm. I just want to be symmetric with this thing. So answer, begin. No, iterator type, I don't need it because I have the tree, right? I don't need the two iterators. The tree already stores all the points. So I need the query and scalar norm. That's it. Now, first case. Case number one, if the number of points, so if we are in a leaf, then we have to carry on a brute force search, right? So, how do we know that we are in a leaf? We have the left and the right pointer. If they are null pointers, then we are in the leaf. Can we reuse the brute force search? Come on. Where was it? Here? I can just copy it. Root force search.h. Boom. I'm just extracting it and putting on another file. All right. Yes. So in this file, we will have also to include brute force search. No? Brute underscore force underscore search. I typed it on the wrong file. This is the test. Where was it? And this was one. Was the other editor? Here. Brute force search. Brute force. No, force search. The first one was answers. Second one was begin, end, query, and norm. Begin, and was it? Query and norm. Yes, that's it. Return. Otherwise, because this is the fast search. Basically, I'm filling the answers with a brute force search. This is leaf node, so I'm filling the answers with the brute force search on this node because I have too few points and I don't have any. It's useless that I go to the left and to the right. The other case, what can I do? This is the distance from the splitting plane, right? You remember? I take the query, I subtract the mean, then I project this vector onto the plane normal. If I get a positive value, then I am one side of the plane. If I get a negative value, I'm on the other side. Interestingly, I also have the quantity of the distance. So I could decide whether to carry on the search on both leaves, or only one, or only on the other. Let me, because I made a okay, was not this. I have go first. How was it? How was it? Because I want to be consistent with the plane direction, to the plane side. So sometimes I define the positive distance goes to the left, and some other times I define the positive distance going to the right, and they have to match. So I want to see. Okay, so negative is to the left. Query minus center. Query minus center. North center minus query, and distance from the split plane. Okay. Query. How was it? Query minus center. Okay, query minus middle. Middle or mean? No, mean, not middle. Mean. Middle is something that I don't have it here, right? Mean, I called it mean, the mean point. So if it's smaller, I have to go to the left. If distance from split plane smaller than 0, now we have learned it. Left, fast search, answers, query, norm. Answer. No? How to turn this search in a complete search? Smaller than norm, right? You search only on the left. If it's else, if smaller than norm, this is a full search. Else, if the distance from the split plane is greater than minus norm, is smaller than minus norm, you search only on the left. If the distance is greater than plus norm, then you search on the right. If the distance from split, you search on the right. Otherwise, what is the third case? The distance is comprised between minus norm, and so you could easily do and clearly it's not called anymore fast search, it's called full search. Fast, full, boom. Right? Powerful, eh? Now I don't know whether it compiles, now I will have some fun, and I don't know whether it's correct, but let's see. Of course, I change, every time I implement something, I do it slightly different from the previous time. In the example that I put into the code, I just like parameterize the KD3 over a container, which is less flexible than parameterizing it between begin and end. Okay, between two portions. But I will have to copy the test, KD3, my funky KD how was it? KD3, eigen KD3 test. Okay, and then we will file save as funky test. Funky test. For funky test, I just don't need anything. Brute force search, I already put it here. Container type. This is the fast search. I've been consistent. Okay. No. No. Easy. Okay, I need clearly to change the CMake list. Like what in the main file, what will I do? Eigen KD3 is called my funky business, right? My funky KD3. My funky KD3. I have a short-term memory of it. Yeah. My funky KD underscore 3. Will it compile? Now we will struggle for some minutes in getting the templates compiling. Edit the CMake lists, and we have to add another executable. My funky test, how was it called? Here you see, short-term memory, funky test. Oh, Alt X compile. Build. No, niente. Build? Niente. Ah, because I don't have a build directory. Okay, clearly. Now you digest it, and let's see. This is easy.
Also, you called server normal.
Yeah, let's see. Underscore normal. That was easy. Pile. Member function, what do we want? Normal, you're right. I'm being systematical, right? Like, probably because I copied and pasted it. Oh, all right. Okay, let's see whether it works. Probably it will crash, right? Funky test. No, it works. How comes? All right. What is the funky? Then clearly I will put on in your solution funky test, right? We coded it somehow in class, and then now we have 10 minutes. Let me run some jokes, right? Let's see how much do I gain, and so on. Now, what I do in this test is I generate 100 points. 1,000 points, a certain number of points. Now, 1,000 is a name that, to me, it sucks. I write int num points, so that equals 1,000, and then I run a query replace 1,000 with num points in the reminder, because in this way I can do some more tests without, constants in the programs. No. Better. Okay, and then we generate these points in a ball. Eigenvector points we define, first of all, define a container type just for clarity. We say we have a vector of 3D points, just for simplicity. We define a 3-node type by 3-node, which is a 3-node. We remember that we templatize the 3 on the iterator, so container type iterator. Okay, container type. So it will be instead of an iterator of this business over here. Okay. Fine, and then we resize the vector to 1,000 or to the number of points, and we generate for each of these vectors that we scan through reference, we generate a random vector, and we multiply it by 100 to give it a little bit of a scaling, because the random function produces values between -1 and 1. Okay, to make it a little bit larger. Otherwise, 0.0, it becomes stupid by watching the points. Then we construct the tree. Isn't it beautiful? Begin, end, and 10 points in leaf. And we have a tree. That's the tree object. It did everything. It did the recursion, the splitting. Clearly, it reorganized the points in the vector. And now they don't have the very same order. Now they are all shuffled to comply with the tree. In the tree, we didn't put the copy of the points. We just put the begin and the end, relying on the fact that the split is going to sort them. Okay? And then we start doing a search. Here we do a search in a ball radius of 10. And in doing the search, we look for every point, like we use for each point in the KD points, like which were the points that we use to generate the tree. We do a fast search in a ball radius of 10, which means that the radius of the ball has to be 10. And so we declare the number of neighbors. This is answer type. You remember? Answer type is a vector, is defined. What is tree-node type answer type? It's a vector of pointers to the points. And we have to declare it because we're going to write into it. So we say, do me please a fast search, and then it fills in the neighbors. Do me please a full search. Of course, we have to clear them. And then we extract the number of points, full points returned. Do me please a number of true points, which is the complete search returned by the brute force search. And here I just like put an asset, I put a warning in case the number of points returned by the full search is not equal to the number of points returned by the brute force search. Is that clear? And then, therefore, I mean, clearly, depending on the radius of the ball, I might have different answers. If the radius is very small, then basically the fast search will do well, because the radius is small means that in very rare cases you have to do the recursion on the left and on the right. If the radius is very large, then there is a high chance that the ball is cut because it's larger, and so if you cut it, then it's possible that you go on the other side. Clear? So what I print here is these numbers, right? And then with a small ball of 10, everything is fine. Oh, in this case, you can see that the first number is the number of points returned by the fast search. This is the number of points returned by the full search, and this is the number of points returned by the brute force search. I'm doing 100 searches, 1,000 searches. It's quite fast, but let's see what happens if I put 10,000. Right? Yeah. Should do. Of course, it will print a gazillion of things. So right now, I'm interested just in having the timings, right? So let me remove this printout, otherwise it will print 1,000,000 times this line. Why that? So let's say this way, our previous experiment confirmed that the brute force search is equivalent to the full search of the KD tree. Do we agree? Because they were always reporting. And by the way, I print something if this wouldn't be the case. So let me do an example, let me do a test, and let me blast the full search. Okay, because it disturbs me humongously. And then, clearly, this is not going to be true. Neighbors clear is not needed. I'm just doing the very same thing. So now, for every point, I will do a fast and a full search. 10 million. I know why. But okay, that's time. Let's profile it. Let's profile it with a fast search first, and then with a full search later, and then with a brute force. But now we are testing the fast search. This is the fast. Approximate, but like tractable. Let's see the full. Remember that with this huge distance, because 10 over a radius of 100, it's quite a huge distance, then the full closely degenerates to the full closely degenerates to a brute force, at least in a region. But still, it's going to be better. Now we are profiling the full search on a KD3. No, not bad. Did I compile it? No, I was cheating. And then we try to change the radius a little bit. We set it to 5. And then we try also with the full search. 10 seconds. Let's see the full. The brute force business. John. And then we try to change the radius to something which is more reasonable with 1,000,000 points. It's going to return a huge data structure at every loop. Remember that the neighbors, remember that the neighbors are, sì, mo me ne vado. Done? Think 100 seconds. And then I change the radius to 1, and then we will see that the fast and the brute force converge. Of course, it depends on the size of the data. But still, we're going from, this will be 2 minutes or something like that. Let him wait. Or maybe tomorrow we'll be still waiting. Who knows? Oh, of course, it's compiled in release, so the fastest possible. Now, clearly, the example in there is slightly different from the example that from the code that I put on the repo. Once I'm in the office, I will synchronize them so that you have this version of the thing. As an exercise for you, for the next time, it's quite straightforward. I might ask you to implement the methods that in the KD3 that instead of returning the set of all possible answers within the norm, within the ball, only returns the best one into the pool. So I don't return a vector of answers, I just return a point, or a pointer to a point, that is null pointer, clearly if I don't find any, or it's a pointer, good one, if I find a point. Is that clear? Instead of returning everyone, and you don't do it by passing a vector. You rewrite it from scratch, because this method was still computing. All right, I think I have to leave the lecture all to the folks. Let's see here. There are no questions. Very good.